the function f of x equals the absolute value of sine of x between 0 and 2 pi. Okay, this is 2 pi periodic, and I want to take the Fourier series of it. So as usual, I will first find the complex Fourier coefficients c sub n, and then using that I will find the real coefficients a sub n and b sub n. Okay, so as usual, I will compute 1 over 2 pi times the integral from 0 to pi sine of x times e to the minus I n x dx minus 1 over 2 pi times the integral from pi to 2 pi of sine of x times e to the minus I n x dx. Okay, so the first thing I did is split that function into two parts. The part from 0 to pi where sine is positive, okay, and the part from pi to 2 pi where sine is negative. Okay, remember, if you have your circle here, okay, the sign here from 0 to pi in this sense, so counterclockwise, is positive here, and from pi to 0 or 2 pi, okay, 2 pi, here sine is negative. Okay, so I split that into two parts. And now I can rearrange this second part here from pi to 2 pi. I can switch the integral borders, so I can take the integral, like remember, the integral from a to b is equal to negative the integral from b to a. And so if I do that, I can use this negative sign here to cancel with this negative sign here, and so I get a positive integral. Okay, so if I switch the integral borders, okay, I get the plus the integral from 2 pi to pi of the same thing. Okay, now I have a plus. Okay, and so you can evaluate that. I won't do it here. I advise you. So in the last video we used another way of evaluating it, but I noticed that this method is really complicated and tricky, and that there is a much simpler way, is as I already said in the last video but didn't use. Now you can use it. It's much easier to use the formula sine of x is equal to e to the ix minus e to the negative ix over 2I. If I substitute that here and here, I can combine those exponents here with this e to the negative I n x, okay? And so I can evaluate it a lot easier because now I have an exponent, okay? Only an exponent, okay? And so if you can do that, and at the end you should get, once you have evaluated your integrals, you should get the following result. So that is the first part, and that is the second part. I mean, those are the same basically. You get the same thing. You get 1 plus negative 1 to the nth power over 1 minus n squared times 2 pi, plus the same thing. So negative 1 to the nth power plus 1 over 1 minus n squared times 2 pi. Okay. Yeah, so those are the first and second part respectively, and yeah, don't forget this 1 over 2 pi in front of it, which will be here and here. Okay, so then we can combine both, and so we get the same thing, but now we only have pi in the denominator and not 2 pi, because I said this is 2 times the same thing, so we can get rid of a 2 here and the 2 in the above the fraction bar. Okay, because I said those are the same thing, so we just add both of them, and so you can cancel with the 2 in the denominator. Okay, and so we're left with 1 plus minus 1 to the nth power over 1 minus n squared times pi. Okay, and so this whole thing is 0 if n is odd. Okay, if I plug in like n is equal to 9 here, I get minus 1. Okay, because minus 1 to the 9th power is minus 1, and so I get 1 plus minus 1, so 1 minus 1, so 0. And if n is even, I get again 2, because like if n is like, I don't know, 8, I have minus 1 to the 8th power, so I get 1. So I get 1 plus 1, so 2, and so I get 2 over 1 minus n squared times pi. Okay. Yes, and as usual, here we need to be careful about where this whole thing is not defined. This whole thing here is not defined for n is equal to 1 and minus 1, so you need to evaluate them separately. And you can notice at the end you should get 0 for both cases. So in the last scenario we didn't get 0, but here we should get 0 for both, and that makes sense because now sine is defined from 0 to 2 pi, so we are integrating over a whole period. In the last video where sine was only defined from 0 to pi, and from pi to 2 pi we have nothing. At that time we didn't integrate over a whole period, only half of it, so it made sense that we get something non-zero, but here we integrate over a whole period, so it makes sense to get 0. Yeah, I hope you understand what I'm saying. Here we integrate, if you do those computations here, again you replace the n here in the calculation with this 1, respectively negative 1, and do all the computation, you will get 0 because you're integrating your sine of x over a whole period, which wasn't the case in the last video where sine was only defined from 0 to pi, and from pi to 2 pi you had something else, you had 0. Yeah, so you get 0, and so now those are our complex Fourier coefficients, so 2 over 1 minus n squared times pi, and we can find our b sub n, which is defined as I times c sub n minus c sub negative n, which will simply be 0, and a sub n is equal to c sub n plus c sub negative n, and so we get basically the double that, okay? Because for the b sub n, we only have an n squared here, so that we have n positive or negative, we get the same result. But here we subtract the second result from the first one, and because both are, as said, the same thing, we simply get 0. We subtract something from the same thing, so we get 0. Okay, and for a sub n, we add both terms, so it doesn't change anything. So we add both, and because, as said, because we have n squared, that n is positive or negative doesn't change anything, and so we are left with 2 times the thing here, so 4 over 1 minus n squared times pi. Okay, instead of 2 over 1 minus n squared times pi. Okay, we have doubled the amount. Okay. And so our Fourier series, real Fourier series, will be defined as the sum from n is equal to 0 to infinity. Notice we begin at 0 because, as I said here, n equals 0 is not the problematic case. We can do it. It is n is equal to 1 and negative 1 that are problematic, but not n is equal to 0. So you can begin at n equals 0 for the a sub n. Yes, so we get the sum from 0 to infinity, of a sub n times cosine of nx plus the sum from n equals 2 to infinity. Why? Because the b sub n usually starts at 1, because there is no b sub 0, because we simply get 0 because we have sine of 0 if you plug in n is equal to 0 here. And for the 1, this is, as said, the 1 that is problematic. Like your b sub 1 would be defined as I times b 1 minus b sub negative 1. But because both b sub 1 and b sub negative 1 are 0, we simply get 0. So this is the 0 that I've written here at the end. So we can begin at 2, n equals 2, and so we have the sum from n is equal to 2 to infinity of b sub n times sine of nx. And yeah, in fact, all the b sub n are also 0, as we said here. I didn't know why I didn't say it before, but yeah, so this whole thing actually is also 0, so we don't really care about it. Yes, but you cannot include this 0 that comes from this b sub a here inside, because as said, it is not defined if n is equal to 1 here, okay, respectively 1 and negative 1, because as we saw here. So you cannot include it in the sum. Even if both are 0, you cannot include it here inside, because, yeah, as said, it wouldn't be defined, so it wouldn't be corrected. It wouldn't be correct to write it like that. And so at the end, you are only left with the a sub n. So we get the sum from n is equal to 0 to infinity of 4 times cosine of nx over 1 minus n squared times pi. Yes, and so that is our final result. And remember, n is even. That's what you saw here. If n is odd, you simply get 0 for the whole thing, and that's not what you want. So you could, if you want, let n is equal to 2m, where m is an integer, so you can make sure that n will always be even, because something times 2 is always even, and so you can rewrite this stuff if you want. The sum from m is equal to 0 to infinity of 4 cosine of 2mx over 1 minus 4m squared times pi. Okay, so that's the same thing as here, just you replace every n with 2m. Okay, and so yeah, m equals 0. Yes, or not? Yes, sorry. And so that would be your final result. So the sum from m is equal to 0 to infinity of 4 times cosine of 2mx over 1 minus 4m squared times pi. That would be your final result. So as usual, same thing. You split here your function into both parts, so the positive and negative parts, because you have an absolute value. And we find the complex Fourier coefficients. Here we need to use the formula sine of x is equal to e to the ix minus e to the negative ix over 2I. So as I said, you can do like in the last video, but it is really complicated, and in fact it's true, this formula really simplifies a lot of things. So you are a lot quicker and easier. It's a lot quicker and easier to deal with that, and you make probably less errors. So you evaluate those complex Fourier coefficients, and you get your result, and then you say, okay, this is defined for n is odd or n is even, depending on the case, and then you find you calculate the integrals for the n's that are otherwise undefined. Okay, where you would divide by 0, you do those cases separately. So here we have c sub 1 and c sub negative 1, and then you find your real Fourier coefficients using the complex coefficients that we just found, so the b sub n and the a sub n. Here I said our b sub n is 0, also our c sub 1 and c sub negative 1, so the problematic cases for n are also 0, because we are integrating over a whole period of sine, but that is just yeah, that's why we couldn't foresee that it's like that. So even if it's 0, if you don't do it, you will probably use points in exams, because we cannot know that we will get 0. Okay. Yes. So and yeah, for the a sub n, I said you get 4 over 1 minus n squared times pi. And so we have a Fourier series, a real Fourier series. We begin at 0 and we go on to infinity. So the sum from n equals 0 to infinity of a sub n cosine of nx, and I said this whole thing with the b sub n here is 0. Yes, and so we are only left with the a sub n, and if you do that, you have the sum from n is equal to 0 to infinity of 4 times cosine of nx over 1 minus n squared times pi. And yeah, I said, remember here n is even, I said here, so you can rewrite it if you want as n is equal to 2m, where m is an integer, so you make sure that your n will always be even. And if you rewrite it like that, you get this result here. So that's the same thing, but just in a slightly changed. So you have the sum from m is equal to 0 to infinity of 4 times cosine of 2mx over 1 minus 4m squared times pi. So that will be your final result. Yeah, so I hope I forgot nothing. Yes, and I hope it was clear and that you could read it. And yes, thanks for watching.